All right, let's just jump right into it. Today, we're completely cracking open the black box of the Advanced Encryption Standard, or, as we all know it, AES. Now, if you're watching this, you probably already know that AES is the absolute gold standard for data protection. I mean, it's used by major cloud providers, it secures your operating systems, and it protects the foundational networking protocols we all rely on every single day. But here's the really critical problem. If you just blindly plug AES into your application without deeply understanding its underlying modes of operation, you are setting yourself up for some absolutely catastrophic system breaches. So in this explainer, we are going to learn exactly why that happens and, much more importantly, how to actually use it the right way.
Here is a quick look at our roadmap for today's explainer. First, an introduction to AES encryption. Then, the flaws of ECB mode. Third, chaining blocks with CBC. Fourth, GCM and authenticated encryption. Fifth, using AEAD in practice. And finally, an AES best practices checklist.
Okay, Section 1, Introduction to AES Encryption.
So, before we get into the incredibly complex modes of operation, we really need to establish a rock-solid baseline of how AES actually processes your data under the hood. At its core, cryptography is completely about transformation. We always start with plain text. This is your original, perfectly readable data. A cipher then uses a specific algorithm and a highly guarded secret key to transform that plain text into ciphertext. This ciphertext is completely scrambled. It's unreadable to absolutely anyone who doesn't possess that exact same secret key. And decryption? Well, that's simply the exact same process running in reverse. But how exactly does AES achieve this level of scrambling? It doesn't just shuffle things around at random. It relies on this beautifully complex mathematical substitution and permutation network initially known as the Rijndael cipher. This algorithm basically treats your data like a mathematical grid, applying intense, highly structured chaos to ensure absolutely no recognizable pattern survives the transformation.
Now, you have to remember that AES is a symmetric cipher. That simply means the exact same key is used to both lock the data during encryption and unlock it during decryption. But the defining characteristic of AES is that it is a block cipher. The algorithm strictly requires its input to be fed in fixed 128-bit chunks. That is exactly 16 bytes. If your data happens to be shorter than 16 bytes, you have to pad it. If it's longer, you have to chop it up. Let's conceptually open up this black box and look at the engine for a second. When a 16-byte block enters AES, it gets arranged into a 4x4 grid called the state. The algorithm then runs this state through multiple rounds of mathematical transformation. Depending on your specific key size, it'll run 10, 12, or 14 rounds. And in almost every single one of these rounds, 4 distinct, highly powerful operations take place. First up is subbytes, which is a nonlinear substitution step where every single byte is swapped out using a predefined lookup table called an S-box. Next is shift rows. This is a transposition step where the rows of our 4x4 grid are cyclically shifted over, totally scattering the data. Then comes mix columns, a really complex linear mixing operation that mathematically combines the 4 bytes in each column, ensuring that a change in just one single byte cascades across the entire block. Finally, add round key takes a piece of your secret key, which has actually been expanded into a whole schedule of subkeys, and bitwise XORs it right into the grid. This intense, repeating cycle creates a mathematical avalanche effect. A single flipped bit in the plain text completely morphs the final ciphertext. That chopping up and intense internal processing, that is where the real security engineering begins.
Moving on to Section 2, the flaws of ECB mode.
So, a natural question arises. How exactly do we encrypt a file or a message that is way, way larger than a single 16-byte block? Well, the answer lies in what we call the mode of operation. This is the method we use to apply the cipher to multiple blocks. The most basic mode you might instinctively think of is called electronic codebook or ECB mode. In ECB, the system simply chops the input data into independent 16-byte blocks and then encrypts every single block individually using the exact same symmetric key. They are just lined up, encrypted, and concatenated back together. Sounds pretty simple and straightforward, right? But this simplicity actually introduces a massive, fundamental vulnerability into your system.
The fatal flaw of ECB comes down to one thing: deterministic patterns. AES itself is entirely deterministic. If you give it the same input block and the same secret key, it will always, 100% of the time, spit out the exact same ciphertext block. Let's think about a real-world example. Imagine you are encrypting HTTP requests and responses. Every single successful HTTP response begins with the string HTTP/1.1/200 If you count those characters and add the new line, it equals exactly 16 bytes. Because of ECB's deterministic nature, an attacker who is just passively monitoring the network traffic will see the exact same scrambled ciphertext block repeated every single time there is a successful web response. They don't even need to crack your AES key. There is no brute force required here. They literally just spot the repeating pattern, copy that specific block of ciphertext, and overwrite the error responses in the payload with that 200 block. Just like that, they've manipulated the system without decrypting a single thing. This is exactly why you must never ever use ECB mode in production.
Let's look at a better way in Section 3, Chaining Blocks with CBC.
So how do we actually fix ECB's predictability problem? Cipher block chaining, or CBC, was engineered as the evolutionary upgrade to completely defeat those repeating patterns. To prevent identical plaintext blocks from creating identical ciphertext blocks, CBC introduces something called an initialization vector, or IV. This is a purely random 128-bit value that gets mathematically mixed with the very first block of plaintext before the encryption even happens. Then, the real magic kicks in. The resulting ciphertext of that first block is fed forward and acts as the IV for the second block. This chaining process continues down the entire line of data, completely randomizing the output. When you think of the CBC mental model, you feed it plaintext, the key, and the IV. It then outputs the IV in cleartext, so the receiver actually knows how to start the decryption process, followed by the highly randomized ciphertext.
But listen, I need to deliver a very, very high-stakes warning right now. If a key and IV combination is ever reused, you can end up with catastrophic encryption failure. An initialization vector is what cryptographers call a nonce, literally a number used only once. It must strictly be generated randomly and used only a single time per key. If you reuse an IV, all of that beautiful randomization we just talked about completely breaks down and attackers can begin mathematically recovering your plaintext. It's a huge deal.
And to be honest, even if you manage your IVs absolutely perfectly, CBC mode still has a fatal limitation. Security researcher Andrew Tierney actually demonstrated a fascinating vulnerability with this. Imagine you encrypt a text file that says, "a dog's breakfast," using AES-CBC. Because CBC only protects the confidentiality of the data, it completely lacks what we call integrity checks. So an attacker who intercepted the ciphertext could literally flip random bits in the file. When the receiver gets it and decrypts it, the file might now read "a cat's breakfast." The attacker didn't know the secret key, they didn't break AES, they just tampered with the ciphertext because CBC mode blindly decrypts whatever you hand it, even if it's been manipulated in transit.
That brings us to Section 4, GCM and authenticated encryption.
That bit-flipping limitation highlights why we need a system that doesn't just keep secrets, but actually guarantees the mathematical truth of the data. Think about the fundamental goals of cryptography for a second. AES-CBC gives us confidentiality for sure, but it fails completely on integrity and authentication. This is exactly why the industry moved to GLOS/counter mode, universally known as GCM. GCM is the absolute supreme standard today because it provides all three. It gives you confidentiality, so the data is completely secret. It gives you integrity, so you know the data hasn't been altered. And it gives you authenticity, so you know it actually came from the person who holds the key.
The way GCM achieves this is by generating a brand new output, the authentication tag. During the encryption phase, the GCM algorithm mathematically calculates this tag based on the ciphertext. Then, during decryption, the very first thing GCM does is look at that tag. If even a single, microscopic bit of the ciphertext has been tampered with by an attacker, the authentication tag will mathematically fail to match. So instead of decrypting a corrupted file and causing total havoc in your application, GCM will just throw a hard error and absolutely refuse to process the file. It acts as a built-in, unforgeable, tamper-evident seal.
Now for Section 5, using AEAD in practice.
It's one thing to understand the theory here, but how does this actually apply to complex, real-world networking and database systems? Because in the real world, systems constantly need to read unencrypted routing headers just to figure out where a message should go, while simultaneously verifying that the encrypted payload hasn't been detached or modified along the way. Historically, developers tried to manually glue these concepts together using message authentication codes, or MACs. It was a mess. They tried these highly complex combinations. First, there was encrypt in MAC, which early SSH used, then MAC then encrypt, which was used by older TLS versions, and finally, encrypt then MAC, used by IPEC, which was definitely the most secure of the manual methods. But the problem was, combining a hashing algorithm for the MAC
with a totally separate encryption algorithm for the body, was incredibly fragile. It was so prone to subtle, devastating security bugs. The industry desperately needed a revolution.
And that revolution arrived as Authenticated Encryption with Associated Data, or AEAD. AES-GCM fully supports AEAD right out of the box. The way it works is brilliant. You feed the algorithm your secret payload to be encrypted, but you also feed it additional data in plain text, like an IP address or a routing header. GCM will leave that header totally unencrypted so your network can read it, but it will compute a single, unified authentication tag over both the plain text header and the encrypted ciphertext. They become cryptographically bound together forever.
Let's unpack a highly relatable scenario to show you why this binding is just so powerful. Imagine a database attack. You have a table storing transaction IDs and encrypted credit card numbers. A malicious database administrator wants to cause some serious chaos. Now, they don't have your AES key, so obviously they can't decrypt the credit cards. But what if they just copy the encrypted credit card data from row A and paste it right over the encrypted credit card data in row B? They are literally just swapping data around. If you only use standard encryption, your app would eventually just blindly decrypt the wrong credit card for that user. But if you use AAED, you can actually use the transaction ID, the date, and the amount as the associated data. When the attacker swaps the encrypted cell to a totally new row, the authentication tag will check that new row's transaction ID, realize it doesn't match the original mathematical binding, and throw a hard error. AAED stops data swapping attacks completely dead in their tracks. It's awesome. Finally, Section 6, AES Best Practices Checklist.
So implementation is absolutely everything. But before we get to the final developer checklist, we have to ask the elephant in the room question. What if an attacker has a quantum computer? AES is incredibly secure today against classical computers, but there is a quantum computing method called Grover's algorithm. Grover's algorithm effectively halves the mathematical strength of symmetric encryption keys. So a 128-bit key would theoretically only offer 64 bits of security against a full-scale quantum attack. And in the cryptography world, 64 bits is just not enough. Therefore, to truly future-proof our systems, 128-bit keys will eventually be totally insufficient.
Knowing that quantum threat is on the horizon, here is your rapid-fire enterprise security checklist for AES. Number 1. Mandate 256-bit keys across the board to protect against those future quantum threats. Number 2. When you are using AES-GCM, your IVs must strictly be exactly 96 bits, which is 12 bytes. Number 3. Always configure your authentication tags to their maximum 128-bit size for peak security. Number 4. Generate your keys and IVs using a cryptographically secure random number generator. If you're in Java, that means strictly using java.security.secureRandom. No exceptions. And finally, please avoid trying to manually string all these complex configuration parameters together yourself. Use heavily tested, developer-friendly libraries like Google Tink. They implement all of these exact best practices by default so you don't accidentally shoot yourself in the foot. And that brings us to the end of our deep dive into AES. I really want to leave you with this final provocative thought today. Go back and look at your own code bases and ask yourself this. Are you deploying encryption that only keeps a secret, or are you deploying encryption that actually guarantees truth? Because as we've seen today, confidentiality without integrity is a massive liability waiting to happen. Thank you so much for learning with us, and we will catch you on the next Explainer.